On a sweltering summer afternoon, there's nothing quite as refreshing as sitting directly in front of a table fan as it starts to spin. The mechanics are simple: physical wind. Out on the highway, standing hundreds of feet tall, is a machine that works the other way around. A wind turbine operates in reverse. Instead of consuming electricity to move the air, it allows the moving air to push its blades and uses that physical rotation to generate electricity. Humans have captured the breeze for centuries. Traditional wooden windmills, like the classic Dutch designs, use the wind's pushing force for direct physical labor, spinning heavy stones to grind grain or pump water. Even in a brisk wind, those massive white blades turn quite slowly, often only 15 to 20 times a minute. It looks like a gentle, easy spin. How can a rotation that slow possibly generate enough high-voltage power to light up hundreds of homes? The turbine uses internal gears to multiply that slow movement into the intense speeds needed to create electricity. To see how that works, we first have to look at the blades. These are massive, aerodynamic structures shaped like airplane wings, designed to create lift as the air flows over them. Surprisingly, these gigantic blades are not bolted rigidly in place. They can rotate along their own length, twisting back and forth depending on the weather. By adjusting this angle, the blade's pitch, the turbine catches the maximum wind available. It's also a vital defense. During a violent storm, the blades feather entirely flat, letting heavy winds slip right past, keeping the turbine from spinning too fast and causing damage. Because it can constantly adjust its blades to match the weather, the turbine acts as a reactive machine, responding to nature in real time. This schematic takes us inside the outer casing, the nacelle. Here, we see how the machine converts motion into power. Right behind the hub is component 4, the low-speed shaft. Bolted directly to the blades, it turns at a sluggish 20 rotations per minute. That brings us to our core problem. 20 rotations per minute is far too slow to generate commercial electricity for the power grid. Think about riding a bicycle. When you shift gears, a large gear connected to your pedals turns a much smaller gear on the back wheel, making it spin much faster than your feet are moving. Component 5, the gearbox, does the exact same thing. It takes that sluggish 20 rotation per minute input, runs it through interlocking gears, and outputs a steady 1500 rotations per minute. This fast spinning shaft drives component 6, the generator, whipping magnets around coils to create electrical current. The gearbox is the critical bridge. It links the slow, massive forces of nature to the high-speed demands of our electrical grid. But there is one more major challenge. The wind rarely blows from the same direction all day. If the wind hits the side of the blades, they won't turn efficiently. To solve this, a yaw system rotates the entire housing on top of the tower, tracking the wind. On the back, a wind speed sensor and wind vane at numbers 8 and 9 tell the motor exactly when to rotate into a better position. With sensors reading the air, the yaw turning the head, and the pitch angling the blades, the machine operates on its own, tracking the weather without human intervention. From that generator high in the sky, electricity travels down thick cables hidden inside the tower and routes directly into the local power grid. When dozens of these machines are grouped into a wind farm, they pool their output to provide clean, renewable energy to thousands of homes simultaneously. It takes 3 distinct steps: smart blades capturing the breeze, gears multiplying the speed, and magnets generating the power. Next time you see these machines in the distance, that slow rotation won't look so lazy. You're seeing a high-speed power plant at work, harvesting energy directly from the invisible currents of the sky. If you enjoyed learning how the machines around us actually work, hit the like button and subscribe. We'll see you in the next video.